Hello everyone, welcome to another kinetic tutoring episode, and today we have a little bit of a different type of video. So I'm going to be responding to this question from Habanero Chi, where the commenter asks, how would one find the differential equation of motion in the first place? And this response was left under a video where we were looking at the equation 2d squared theta over dt squared is equal to negative 0.5x, which we can simply write as d2 theta is equal to dt squared is equal to negative 0.25x. All we did here was just divide both sides by 2. So of course I'm going to be showing you how to find d2 theta over dt squared in different scenarios. Now, the first thing you want to keep in mind is that d squared theta over dt squared is simply just going to be angular acceleration, or alpha. And the reason behind this is because d2 theta over dt squared is the second derivative of angular position, which is angular acceleration. We have theta, and when you take the derivative of theta, you're going to get omega, and when you take the derivative of omega, you're going to get alpha. So let's rewrite this problem. It's simply saying 2 alpha equals negative 0.5x. Alpha is negative 0.25x. Now, how did we get this alpha? This is very simple. There are different equations in which you can get alpha from, but let's just use the two most common examples, which is going to be a simple pendulum of a point mass that is oscillating, or a spring that is oscillating. So let's just get straight into these problems, and I'm going to show you how you would solve for alpha. And we're going to start with the spring first. So the first thing you want to do when solving for alpha, or in the spring's case, it would be A. So for a spring, it would be d2x over dt squared, which is otherwise written as A, or just regular acceleration, because when you have a regular spring system, it is oscillating in a linear manner, whereas when you have a pendulum, then it's going to be alpha because it's oscillating in a rotational manner. So let's get into this spring example. The first thing you're going to want to start with is the restoring force. We know that our force equation is mass times acceleration, and our spring force is negative kx. And so as you can see here, we can already set up an equation for acceleration. You just move the m over to the other side. Negative k over mx. This is one way you could find your acceleration if you're given your spring constant k and your mass m. This is all you need to do. But let's say you were given like a period or something like that. In that case, you would need to look at your equation in terms of time. And so we're going to have to look at our displacement in terms of time equation. And the basic equation for displacement in terms of time of a simple harmonic motion spring is going to be A sine or cosine. It doesn't matter which one you start with. Sine just means it's starting at a position where it is not displaced, and cosine means it's starting at a position where it is fully displaced. And so from here we can find our acceleration by taking two derivatives. We know that acceleration is the second derivative of position, so let's do that really quickly. The first derivative will give you v of t, which will be a cosine omega t times the derivative of the inside here, which will be omega, and a t will give you negative a sine omega t times the derivative again, which is omega, times the omega we had from the velocity equation, omega squared. As you can see here, our x is a sine omega t, and we have a sine omega t at the bottom here. So of course we can just swap out this a sine omega t with x, and that will give us a of negative omega squared times x. Now when you look at these two problems, you'll notice that they look pretty similar. So let's set these a's equal to each other. And keep in mind that if you're given omega, here's another way that you can set up the differential equation. You would just plug in your omega, square it here, and rewrite this as d2x dt squared, and there you have it. But let's go into greater detail. We know that negative k over mx is omega squared, negative omega squared x. We see that two terms cancel here, our x's and our negatives. And if we want to solve for omega, it'll simply be square root of k over m. Now, if we're given the period, we know that our period is simply 2 pi over omega. This is just a formula you're going to have to memorize. So if we're given our period, let's say it's 5 seconds, then we know that our period is going to be 5 is equal to 2 pi over our omega here. And from there you can solve for your k or your m, but you're going to have to know one of them, or else it's going to be an equation with two variables. So that's how you would solve it in case of a spring. Now let's look at it in case of a pendulum. In case of a pendulum, we're going to be using d2 theta over dt squared is simply alpha. Now, here we're dealing with torque instead of force. The torque is going to be applied here because we're assuming this rod or string does not have a mass. So the entire mass is concentrated right here. And we know that the equation for net torque is I alpha, which is equal to force times radius times sine theta. So from here, let's take a look at our force. Our force is simply going to be the gravitational force mg. Our radius is going to be the length of this rod, massless rod or string. So we'll have I alpha is equal to mgl sine theta. And usually when we're doing oscillations of a pendulum, it's going to be of a small angle, so we can use the small angle approximation, which states that sine theta is approximately theta, so we'll just write sine theta as theta. And we're going to move our inertia over to the other side. We're going to divide both sides by inertia to get alpha by itself. So we'll get mgl over I times theta. And as I explained beforehand, this theta is due to a small angle approximation. When we have inertia, we take a look at the inertia of the system, and since this rod or string is massless, the inertia of this simple pendulum is just the inertia of this point mass, and we know the inertia of a point mass is mr squared, and in this case our r is L. So let's write that out. Alpha is mgl over our inertia of ml squared theta. So from here we see this cancels with this. One of our L's on the bottom cancels with our L on the top, and we'll get a alpha of g over L theta. And if you're given L, we know that our g is approximately 9.81 meters per second squared. So if you're given L, you can plug this in to get a differential equation and rewrite alpha as d2 theta over dt squared. But say you aren't given the length. Let's go over the same process of what we did in the last equation. So I'm going to erase all of this here. I'm going to rewrite what we discovered. Alpha is g over L theta. And now let's take a look at our displacement in terms of time. We know that in this case it's angular displacement, so we'll use theta is a sine or cosine. Again, we're going to go with sine omega t. Next, we'll have angular speed omega, a cosine omega t times the derivative of the inside omega, and we'll get an alpha of negative a sine omega t omega squared. Once again, a sine omega t, which is theta, can be moved down here. Alpha is negative omega squared theta. And you may notice that the negative does not cancel out in this case, but this is not too important, seeing that in an oscillating motion there's no real constant direction, it's just oscillating back and forth, so we can really ignore the negative, and we'll get that G over L theta is equal to omega squared theta, and for solving for omega, that'll be square root of G over L. Once again, you can use your period equation, t equals 2 pi over omega. So if you're given t, you can solve for your omega here, square it in order to plug it into this equation. Alpha is equal to omega squared theta in order to get your differential equation. I hope this clears up your confusion. If not, make sure to leave another comment and I will make sure to address it as soon as I can. If you are not this commenter and this helped you anyways, make sure to leave a like and subscribe. That would help the channel a lot. And that's all I have for you guys. Thanks for watching.